Earth is tilted by about 23.5 degrees. We learn that number in school because it explains seasons. But today, I want to ask a different question. What if that tilt didn't just change sunlight? Quick disclaimer up front. This video is an exploration. I'm not claiming a new discovery, and I'm definitely not replacing plate tectonics. What if it also nudged how our planet moved, cooled, and organized itself long before the continents looked anything like they do now? I'm building a hypothesis, then we'll talk about what evidence would support it, or kill it. By the end, you'll understand three things: what a craton is, why it matters, and what kinds of real-world patterns we would need to see for the tilt and swirl idea to even be plausible. And if it isn't plausible, you'll know exactly why. Let's turn this into a documentary for a second. If continents really drift, the Atlantic Ocean is the biggest crime scene on Earth, because it looks like someone split a supercontinent down the middle and erased the seam with water. You've probably seen the classic image. South America kind of fits into Africa like a puzzle piece. It's tempting to stop there. But geologists don't trust coastlines. Beaches move, sea level changes, rivers dump sediment. The edge you see on a map is not the edge of the continent. So what do you match instead? You match things that don't wash away: the ages of rocks, the patterns of mountain belts, and the deepest cores of continents, the Cratons. In other words, we're not going to solve this by dragging continents around until the shapes look good. We're going to treat the Atlantic like a ripped photograph and use the oldest paper in the photo to line it back up. Here's the storyline. Today, South America and Africa are separated by thousands of kilometers of ocean. But if you rewind geological time, they were neighbors, part of a southern supercontinent called Gondwana. First, do the simple visual. Slide South America toward Africa until the margins line up. Now do the grown-up version. Overlay simplified Craton blocks, the ancient cores that are billions of years old, and see how the deep pieces can be reconstructed across where the Atlantic is now. On the South American side, one famous ancient core is the São Francisco Craton in Brazil. On the African side, you have ancient cores like the Congo Craton, and farther northwest, the West African Craton. Don't worry about memorizing names. The point is that these blocks are old, stable, and geologists can track them through time. The next level is when you notice that it's not just blocks. There are long, stretched-out scars, old mountain belts and deformation zones that can be traced from one side to the other in reconstructions. That's the kind of evidence that makes continental drift feel less like a theory and more like a solved case. And this is why Cratons matter for our bigger question. If you want to ask what shaped continents early on, you don't start with coastlines. You start with Cratons, because they're the parts that remember the earliest chapters of the story. So how do you go from neighbors to separated by an ocean? Not by continents swimming around, by a plate splitting. The simplest picture is a crack that turns into a rift valley, then a narrow sea, and eventually a full ocean. In the middle of that new ocean, you get a mid-ocean ridge, an engine that creates new seafloor. As that seafloor spreads, the continents ride away from each other. The edges that face the ocean become what we call passive margins. Not quiet in the deep past, but quieter than active plate boundaries like the Pacific Ring of Fire. And here's the documentary twist. Once an ocean opens, it doesn't just separate land, it separates evidence. Mountain belts get cut in half. Rock provinces end up on different continents. And the only way to reassemble the story is to follow the oldest, most consistent pieces. Again, Cratons, ages, and structures.